Okay. Yeah, I noticed some people asked some questions on the discussion forum, but I'll answer them after this lecture or this afternoon. Yeah, if you have any questions on the assignment or the labs, just ask them on the discussion forum anonymously if you like. In that way, if you have a question, a specific question, it's possible that other people in class will have the same question. So you might just ask it in a place that everyone else can see it, so I only have to answer it once. And also it's more fair as well, so I'm not giving insights secretly into anyone on any of the questions either. Okay, so the last day we're looking at the Linux terminal, and I pretty much finished the slides. We got to this point, scripting and automation. So just at the very end of the class, I had mentioned that the last year's exam anyway had a question just to check your Linux terminal skills. So I won't go through the last year's exam paper now, but I will go through some of the questions later this week or next week. But just to give you an idea of the type of questions, this is question 19. So last year the exam had 20 short questions, and you're not expected to write essay type answers. They're essentially kind of bullet point answers. If you just give the information, you get the full marks. And they're normally designed either as 4 or 6 or 8, where you kind of get, if there's 2 parts, if you ask for 2 things, I don't know why that's doing that, you'll get 2 marks for one and 2 marks for another, so you can get part questions. Oh, I don't know why that's doing that. Let's check. Yeah, I can try to turn it off. The cable's obviously working, so sorry about that. Okay, I'll turn that back on again. So look at this one for now. So there's 20 short questions, and the exam will be the same this year as well. That kind of cover theoretical and some practical aspects of the course. So just to focus on this specific one, it said examine the sequence of terminal bash commands below and give the output from the final command. So this final command here. So we can just go, I'll just quickly go one by one through these commands and see what they're doing. So cd/temp. So /temp is just some folder on a computer. Most Linux computers will have a /temp folder. Temp is in a temporary folder. So some softwares, programs, when they're running, they need to be able to temporarily write things. So they will often have this folder. So go inside that and then make a directory called example. Okay, so maybe I'll just do this as we go. Okay, ooh, oops. You got a bit bigger. So we made a directory called example. Okay, so on my Mac, there's some other these, I don't know what these are. Some program is making those. So I have an example folder, then cd into example. Then first command here, echo, and then there's quotes. So everything inside the quotes is echoed. So if I just do the echo part without anything else, echo just means printed screen. So if I just go echo, this is my first script, you can see it's printed to the screen. But with the greater than my script, it means take that and put it into a file. So you can see now I have a file called my script. And you can see it just put it in. And hash as well as a comment in bash as well. So if I were to just, for reference, paste that here, it does nothing because it's just a comment. It starts with a hash. It's a comment. Then the next thing, it goes echo pwd my script, and it's greater than, which means append to a file. So if it's just 1 greater than, it means overwrite the file. But if it's 2, it means append to the file. So we can try that one. Open up the script. You can see it's just appended pwd to the bottom. And do the same with back command, echo ls. So if we check our file now, you can see this is my first script, pwd ls. Then it makes a directory called backup. Then it copies my script to backup. So we ls now, we just have my script here. Then we have backup folder with a copy of it. And then chmod adds permissions, so to the user or owner, that they can execute the file. So +x means plus it can execute. And because to be able to run a script, you have to do that. So if I go inside, let me see what it says. Okay, so then the last command, which is what you have to give the output of, is it CDs into backup. And then this part here is the only thing that we didn't cover that was in the last slide. So if you want to string commands together, ampersand, ampersand, this is an ampersand, which is like an and symbol. You have two of those at the end of the command. It just means execute the next command if the first one was successful. So it's a way to string commands together. You can use a semicolon, which means execute the next command regardless of whether it's successful. So if I execute that, it's going to cd into backup and then execute /my script. So run the my script. And then this is the output. So where did that come from? If I open up my script, it's going to run this as a set of commands by executing the script. So the first line is a comment, does nothing. The second one, PWD, prints out the current, print the working directory, and then ls, what's in the current directory. So you can see by going my script, it's PWD. It's basically the same as just running PWD here. And then it is typing ls, essentially, which is showing that there's just the my script file. So to get all full 6 marks in this case, you would just have to write out these couple of things here. You got one of them right, you might get half marks. If you got them both wrong, but you wrote out some content that helped me see that you mostly understood the logic and you just missed something, then you can get like you could get a good chunk of the marks. So I'm looking to give people marks. So I've set it up that I'm trying to be generous in how I grade them. Because the marking scheme is strict. Okay. Yeah, this was just the last slide we didn't cover. If you want to string commands together, command 1, semicolon, command 2, that will execute the second command, or you could string 3, 4, 5 commands together, and regardless of whether command 1 is successful, whereas if you use ampersand, ampersand, a double ampersand, that will only execute the second command if the first one is successful. And then, yeah, there's just some last ones. Yeah, just like this funny t-shirt that you can't see. This is the command. This will delete your entire computer. So, but some useful commands. If you control C, that's to kill, interrupt the running process. Control R is to search back through your commands. Tab is to autocomplete. You can go up and down to see previously typed commands. Take care, remove, and then sudo is switch user do. So if you don't give the name of the user, it assumes the admin. So sudo means switch to the admin and do something. And it'll ask for your password the first time you do that. And then some other useful commands as well that you might want to check up. Any other comments or questions? Cool. Okay, so the remainder of this lecture, I'm going to talk a little bit of an introduction to OpenFOAM. So that's the first lab on Thursday this week. On this Wednesday as well, for the first half of the lecture, we're going to have a guest industry lecture as well. A guy from Arup is going to come in. So Arup are like a building services company. They're a British multinational, but they have offices in Ringsend. So they will use OpenFOAM and Fluent and CFD tools for doing. I think the team in Dublin mostly does kind of building analysis. So like designing buildings, looking at the, I don't know, pedestrian comfort and things like that. And maybe fire and smoke analysis, things like that. So on Wednesday, I'll send a reminder about that. For the first half, we'll have a guy coming in. So in my experience from previous years, students really find it useful when guest lectures come in because you get to see how it's connected to what people do in reality as well. And sometimes they advertise jobs as well, if you're interested in going into this area. All right, I will start to talk about OpenFOAM. Okay, so OpenFOAM is the third and final software which we're going to cover in this course, and it's an open source software. So unlike Fluent or Abacus, which are commercial closed source softwares, OpenFOAM is an open source software. So what does open source mean? It means that you can go online and download all the code, it's written in C++, all the code, if you want it. Not many people will necessarily do that. But you can see all the code, and conceptually, or in theory, you could just change any part of that code, recompile it, and have your own version of OpenFOAM to do exactly what you want in practice. Whereas Abacus and Fluent, you can't see the code, you just get the binaries, the executables, which you don't know what the original code looks like. And obviously the binaries are restricted by certain licenses. So even though it doesn't have to be, open source softwares are mostly free, whereas closed source ones tend to be commercial. You have to pay for it. So why might people consider using open source softwares? So probably you could think of a couple of them. All right, I don't know what this thing's doing. I'm going to stand this out. And so there are some reasons why people might use open source software. And cost effective is the first thing you might think of, depending on where you're working. Abacus and Fluent, or ANSYS, one commercial license could cost 40,000 to 50,000 euro per year, a license. So that's like pretty significant. If you're an SME, that would be quite expensive. If you're a multinational, it just would be the cost that you might build in. But that means it's expensive. A lot of work has gone into developing the software, so cost effectiveness is certainly one reason you might consider open source. We're going to look at some disadvantages as well. And particularly now that most computational mechanics softwares now are designed to be run in parallel or run on multiple CPUs or GPUs. So the last lecture we're going to cover in the last lab is about high performance computing. So if you're running a large OpenFOAM or Abacus or Fluent simulation, you might run that in a supercomputer and you might run hundreds of cores. So if you're doing that with a commercial software, depending on their licensing model, they typically charge you more for how many cores you use. So if you have a big cluster with 100 cores, you might have to pay a couple of $100,000 per year to be able to use those to run an Abacus simulation, for example. So to run on one core, it might be expensive, but to run on multiple cores, typically it drops off, it gets less expensive, but it's still pretty expensive. So this is where open source codes like OpenFOAM, there's one argument for why you might use them is the licenses. It's free to download, so then you could run it on 1,000 cores, and it's also free to run on 1,000 cores. So that's definitely one of them. So anybody can use them. And another reason that people might use open source codes is the customization. So as I said, OpenFOAM, you can just download and pack anything. So if there's no boundary condition for your special case, if you have the motivation and the skill set, you can just write that boundary condition yourself. Fluent and Abacus does allow you to customize through user subroutines. So we already saw that for Fluent, we prescribed a parabolic inlet. So it lets you customize in certain limited ways part of the software. Whereas OpenFOAM, you could just pack any part of the solver if you wanted. So for some people, that customization and flexibility is a benefit. Community collaboration projects, these are more secondary reasons. Open source projects, if they get a large enough community base, then you can have multiple groups all over the world developing separate features and they're sharing versions of that. So OpenFOAM, if you go on GitHub, you can find hundreds if not thousands of separate projects by PhD students or postdocs or researchers and companies where they just develop something over a few years and they share it in OpenFOAM. So it might not be in the main OpenFOAM, but it might be some feature that, oh, somebody has looked at molten metal flows and they developed molten metal foam OpenFOAM solver and it solves exactly what I want to do. So that's a potential advantage as well. Transparency and trustworthiness. I don't know how much this matters. People think it matters, but depending on what industry you're in, trustworthiness can be defined in different ways through different standards. So if you have a code that's open source, you can check exactly what's done everywhere in the code. Whereas Fluent or Abacus or commercial codes like that, they'll have documentation that say what they do, but then you don't know what they do. The only way you can check is just run it. You check what answer you get and see if that's consistent with what they said they do. You don't necessarily know exactly what they're doing. Potentially having the code open source, well, if it is open source, it's fully transparent and you can check the algorithms. So that can be a benefit to some people. But okay, a counter argument is as long as you have strict validation or verification test cases, maybe you don't actually have to see the code. Educational value, a lot of times, if you look at finite element or finite volume books, many books that have an applied aspect will provide code with the book. And it's normally something like MATLAB or Python or something that's easier to understand. And the purpose being that it shows how simple algorithms are implemented in practice. So if you have an open source code, it means you can actually go in and we can see how Navier-Stokes equations are actually solved in OpenFOAM, whereas we can't do that with Fluent, for example. So there's an educational value. Cross-platform, because it's open source, if somebody's motivated out there, you can get OpenFOAM to natively build for Mac or Windows or Linux or something like that. Whereas Abacus just said, oh, we're only providing it for Windows and Linux supercomputers. So tough Mac users can't run it. Whereas someone can go out with an open source code and because it's open, they can build it for other operating systems. These are more secondary users, I would say. And then the last two, I'll give relative disadvantages as well. Other arguments for open source. Additional adoption. Okay, this is more as in why you might want to use it. So if there is an open source code that's used in industry, then that might be a skill set you want to pick up. But that's the same argument for any code that's used. So OpenFOAM particularly is used in automotive, maybe less so in aerospace, but particularly automotive. So that can be a useful skill set to have. And R&D, even in larger companies, if they're trying to solve very specific problems over and over again, depending on the industry they're in, it might make more sense to just develop their own custom in-house solver to do that. So for example, I've worked with companies that do metal forming. So Abacus can solve those problems, but Abacus has thousands of features and they just want this one type of problem analyzed over and over and over again. So maybe for them, it would make sense to just have developed a very customized solver just to do that one thing over and over again. And then they don't have to pay for Abacus licenses as well. Challenges, disadvantages with open source software. These are generalizations. Learning curve is typically steeper. So Abacus and Fluent, if you're paying a lot for licenses, so we don't pay 45 or 50,000. They normally will have discounts for academic users. But the learning curve is normally shallower for commercial codes because they have well-developed documentation. Whereas open source codes, somebody's providing something for free, then they're not as motivated to develop really great documentation and training sets. And if you look at business models for companies who develop open source softwares, one way they might make money is through providing paid training. So then maybe there isn't a motivation to provide great free documentation. You just have to pay to get great training. So the learning curve, certainly in programs like OpenFOAM, can be a little bit steeper than programs like Fluent or Abacus. And but okay, you're going to get first-hand information, first-hand experience with that, so you can decide that for yourself. Limited user support. So typically, if you wanted professional technical support, you'll have to pay for it, just like you would for a commercial software. So there might not be as much support, or there might be a smaller user community for some open source codes. So if you get stuck, what do you do? It might not be as clear with some open source codes. Whereas if you're paying for a commercial code, you normally get some basic support with that. So you have someone you can ask if you get stuck. Whereas for open source, you may have to find some company you can pay to provide that support. And then these are kind of related. So documentation quality might not be as good. Once again, these are generalizations. And then software instability, I guess when a code is open source, they may release versions more frequently, and that might mean that the code is less stable. So by stable, I mean you're running a problem, you're getting the right answer, and then the software releases a new version, you upgrade, and now your model doesn't run anymore. Whereas Fluent and Abacus are very careful about how they change any default settings. So the default settings probably haven't changed in Fluent in a long time, because there will be big industrial users who will always benchmark those cases and they want them to work. So they might add features, but careful about changing the defaults. Whereas in OpenFOAM, they might be a bit more, or open source codes, they maybe don't have those same restrictions. And this related to software instability, and I'll comment a little bit on this. So OpenFOAM.org and OpenFOAM.com are two different companies with two different versions of OpenFOAM. So they were the same company, and then people are people, people fell out, and now there's two different companies. But there are other community forks out there as well. So because of the way the license is set up for OpenFOAM, that's open source, anybody can make their own version of OpenFOAM and then advertise that. So it can be a bit confusing for new users in terms of features and comparison. So what is OpenFOAM? First thing, what's with the name, foam? Nothing to do with foam. So once again, it's well, in this case, it's I guess a backronym / acronym. So foam is field operation and manipulation, which is also a terrible name. Doesn't really make any sense. Where they're coming from is in partial differential equations. You normally have fields, as in the temperature field in this room. There's a temperature defined at every point in the room. So the nature of partial differential equations is you're calculating certain field quantities and you're manipulating and operating them some way. So field operation manipulation, you're calculating temperatures, velocity, stress fields. That's the definition. Open means it's open source. So historically, let me just check, do I have the genesis? Yeah, I do, okay. So OpenFOAM started as the foam project, and that was in the late 80s and early 90s. So there's a guy called Henry Weller, and Henry Weller still works and runs this OpenFOAM.org company. So he was doing a PhD in Imperial College in the early 90s. And at that time, C++ was a new language, and it was one of the first languages to use this object-oriented programming concept. So before that, computational mechanics softwares were normally written in Fortran, or it's like procedural languages. And still some of them are. I think Fortran, or I think Abacus is written in Fortran as far as I know. So he was maybe an early adopter of this new, potentially powerful object-oriented programming concept, and he started to create this foam project. And then with a friend of his, a guy called Hrvoje Jacek, a Croatian guy, they started to develop what went on to become foam. So Herv did a PhD as well, and he finished his PhD. Henry gave up on his PhD and just decided to focus on commercializing the software. When Herv finished, they both worked together and they established a company, Nabla, to sell the software. So they actually made a commercial software. Foam was a commercial software, but ultimately a failed commercial software. So in the early 2000s, these guys, two of them fell out, and they decided rather than just letting foam die, they just made it open source. So that was the genesis of foam, was essentially a failed competitor to Fluent. But at the time, though, they had some success. So Fluent actually bought a copy of foam to take the best bits and implement it into Fluent. So behind the scenes, Fluent probably shares certain similarities with OpenFOAM, I would say. There are similar cell-centered fine finding methods. So Henry and Herv, both of them are still around in the OpenFOAM community. Herv makes his own fork of OpenFOAM. I don't think he talks to Henry. He makes another fork. And then this OpenFOAM.com and org split as well. Henry was there. So I get the feeling Henry's probably not so easy to get on with. But anyway, they're released under this GPL. There's many different open source licenses. GPL is one of the most aggressively open source licenses. It's what they call a contagious license. So if you use GPL code in your code, your code becomes GPL by definition. So for example, if Fluent saw something amazing in OpenFOAM, they can't copy it into Fluent because they would have to make Fluent open source. So it's like anybody can use it free, but you have to make your code open source as well. That's the way they do it. There are other open source licenses that let people copy it into the commercial code and they don't have any restrictions. But the particular OpenFOAM code is license is very, let's say, aggressively open source. Historically, OpenFOAM ran through Linux or Unix, but now in the last few years, it's not a big issue to run on Windows through this Ubuntu for Windows, this WSL version. But people have gone out and compiled native Windows installations and Mac versions. I've mentioned a little bit Linux before. Linux is a family of operating systems. So we're using Ubuntu. Linux is the most popular one, but this is OpenSUSE. There's loads of other versions as well. And there's various arguments for why you might use other Linux operating systems, depending on what working on. So OpenFOAM, as you have seen or will see, typically runs through Linux terminal. And that's probably the key practical difference you'll see from Abacus or Fluent, is when you go to run OpenFOAM, you don't have a graphic interface that pops up. You just open the terminal, and then you load OpenFOAM in the terminal, and you run commands in the terminal. Still to see the case in the results, we'll use a graphic program, one called ParaView, which is not made by OpenFOAM. It's an open source visualization software. But that's maybe the key difference. There are graphic interfaces for OpenFOAM. So there's many companies out there who produce and sell to you graphic interfaces for OpenFOAM. So particularly in the automotive sector, you can buy or buy licenses for softwares that in the background just run OpenFOAM, but you're paying for an easy to use interface. Or there's companies like SimScale. So SimScale is a simulation through the browser company. So if you go to simscale.com, I guess, or .whatever, you can sign up for a free account, and essentially you can create a model all in your web browser. And when you go to run it, it's actually using OpenFOAM in the background for the CFD. And they use an open source finite element code for their stress analysis. So one of the features that has made OpenFOAM somewhat successful, and by successful I mean lots of people use it. So there's loads of open source codes out there that nobody uses apart from whoever created it. But one reason that OpenFOAM has seen relatively wide usage is that it can be edited in a relatively simple fashion to solve new types of partial differential equations. So this is the momentum equation from our Navier-Stokes. So for acceleration terms, viscosity diffusion term, and viscous stress terms, and pressure stress terms. So the way this is written in the OpenFOAM solver, IcoFOAM will be just like this. So you might not know anything about C++, but you'll at least see the relationship between each of these terms and a component here. So you can see you have a ddt of u is clearly this one. This divergence of phi u is this. Then you'll have this Laplacian of nu u is this, and then you have grad minus grad p. So for example, if you wanted to add a different term or change the PD, it's relatively simple to go in and edit that. So this is maybe one reason that people have found it, but it's become popular. Distinguishing features of OpenFOAM. When you go to run Fluent or Abacus, that's essentially one executable. In the Abacus and Fluent graphic interfaces, when you create a model, at the very last step, you'll say run the model. But normally at that step, you can write the input file and run it later. So in Abacus, you can go right-click, write input, and it'll make an IMP file. That IMP file is the entire mesh, all the boundary conditions, all the material properties, and it's the model ready to run in one file. So if you want to run that model instead on a supercomputer, you just copy that one file and essentially just run a command line argument Abacus and the input file, and then it will run it for you. And it's the same with Fluent. You'll have Fluent on the input file, and it'll do the same thing. So ultimately, it's like they're running from a command line in the background. It's just a graphic interface is just an easy way to make that input file. Whereas in OpenFOAM, you just have to directly make the input file. So one distinguishing feature of OpenFOAM is in Fluent or Abacus, if you change the settings like transient to steady state or turn on disturbance model or disturbance model, essentially inside Fluent or Abacus, there will be a big bunch of if checks. If steady state, add this term. If transient, add this term. If turbulence is turned on, add this. If else, if it's disturbance model, add this. So it's just a load of if-else checks. Whereas OpenFOAM adopts a different design. It will make separate executables for separate combinations of physics. So if you want to solve what's known as the Laplace equation, it's just a heat transfer equation. There's an executable just called Laplacian foam. And all it does is solve the heat equation. If you wanted to add on Navier-Stokes, you have to go to a different solver. So piezo foam uses this piezo algorithm, like you can choose in Fluent to solve the Navier-Stokes equations. There's also simple foam, which uses the simple algorithm that you could use in Fluent as well. But they're like different executables. There's no if else checks. It's just they code it one way, and then if you want to use it, you use that. Right? And then there's many other solvers. So in OpenFOAM, anytime an executable ends with the word foam, that means it's solving some PDE. They're called solvers. And you can look up standard solvers here for the .com version. They'll have their standard solvers, and the .org version, they'll have slightly different standard solvers. So if the appropriate standard solver is available, then you don't need to develop your own code. So to use OpenFOAM, you don't need to code, you don't need programming, you just need to use a terminal. So most, maybe 95% of all OpenFOAM users will not write or develop their own solvers. They'll just use existing standard solvers. But one appeal of OpenFOAM is that anyone can develop their own applications. And particularly this is appealing in academia, where maybe, for example, in my own research, I'm interested in multiphysics like fluid-solid interaction and coming up with new numerical methods, procedures to solve those types of problems. So in that case, I could just write my own code from scratch, which is a pain, or I could take a code like OpenFOAM and then I can edit in features that I'm interested in. So that's appealing for some people, and there's no licensing costs. But as we said, it doesn't have a default graphic user interface. Interestingly, the original Foam software actually did have a graphic interface. It was called FoamX, and it apparently was terrible. So this is maybe why it failed as a software. But there are, you can see if you go, I think this link is hopefully still up to date. This link GUI, you'll find there's like probably 20 plus GUIs out there that you can use. Some of them are actually free. There are free GUIs. Normally they're linked to a paid GUI. The free version is a simple version, and then you can pay it. So in OpenFOAM, it consists of applications. These are the executables, where you have some of them called solvers. That's actually solving the equations. And then you have what are known as utilities, and they are executables to help set up cases, the pre-process case and the post-process case, so to process results. So for creating the meshes, maybe manipulating boundary conditions, things like that, you will have these utilities. And then in terms of the overall OpenFOAM toolbox, it comes with libraries. So the libraries are just common pieces of code that are shared by all the solvers. So for example, reading a mesh and writing a mesh from your hard drive, that's shared by all the solvers. So that's put into a library. And then one interesting feature of OpenFOAM is it comes with a tutorials folder. So it comes with maybe, I'm not sure how many, 50 to 100 test cases already set up that run. So examples of all the different solvers how to run. So you can just run that test case and then maybe edit it to your particular interest. So OpenFOAM is under this GNU GPL license. So anybody can create their own version as long as they respect the trademark and the license. And there are at least 3 popular forks. So the .org version, which is sometimes called a foundation version. The numbering convention for that, as you'll have seen, this is what we're using. We're using 9. So it's just every year they just release a new version and they just give it the next number. So I think we're at 10, 11, or 12, maybe 11 or 12 now. So 9 will be maybe 2 or 3 years ago. Whereas the ESI version, or the .com version, or it's called OpenCV sometimes as well. I think ESI is bought by a different company now. It's maybe Open, not Open. They use the same convention as Ubuntu. So you'll see 2406. So the first 2 numbers mean the year it's released, and the second mean the month. So 2406 will be June 24. 2312 will be December 2023. So if you're comparing those, they're just different forks, and essentially they just have different features. There's Foam Extend is this Hervoy ASICS community branch, but then there's companies like Engis, Caelus, and other companies who are essentially businesses who have designed their business model around supporting OpenFOAM, providing features for OpenFOAM. And say, for example, Engis, they make a GUI that's used a lot in the automotive sector that sits on top of OpenFOAM, and they have their own version of OpenFOAM as well, with presumably some different features. There's lots of references out there. there's a few books here and just on a reference if this is not so much for this course, but it's if you go on to use OpenFOAM, you might find them useful. One thing which is a little bit weird, you might think, is if you're creating a new model in Abacus or Fluent, you just start from scratch. You draw your geometry, mesh, boundary conditions, material properties, and then you run it. Whereas in OpenFOAM, as you will see, because it's a model consists of a folder or directory of files, you normally start with an existing model, and then you just modify to your needs. So you never essentially start with a blank slate. You'll always start from something existing and edit it. So that's a little bit different, but that's just far more efficient and easier. So normally if you want to solve a problem in OpenFOAM, you find an existing tutorial that already solves something similar, and then you modify the geometry, the boundary conditions, or the material properties to be as you need. So let me see if I can get out of here. Actually, we didn't check this, but do I have OpenFOAM on this? I do. Okay. Should we double check that? Yeah. So just to quickly show you the idea. That's okay. The size of the text at the back, is it? You can see that. Okay. So when you open a terminal, so I think for the computers all upstairs and the instructions I would have given you to install OpenFOAM, by default, it'll just load OpenFOAM. But you can, if you have multiple versions of OpenFOAM set up, you might set up an alias. So you might have seen there that I have OF9, so that will load OpenFOAM 9. Whereas I also have OpenFOAM 1912, which is a different version. So you can set it up that when you open the terminal, OpenFOAM's not loaded, and then you can load a particular version. So there's a few shortcuts that are useful to know. If you write Qt, that brings you to the OpenFOAM installation directory and the tutorials folder. So this, if we type ls, if I type ls here, you'll see what's in that folder. Or if I'm on Mac, I can go open dot and I can just actually see the folder. And that's probably easier to see here. So inside this directory, and actually I've overridden my ls command just to automatically go ls-l and set up colors as well, just to make it easier. So in this directory, these are all example cases already set up. So they break it down into DNS. So DNS is the turbulence modeling approach where you just resolve the mesh. So you can see there's examples how to do in DNS. Some combustion cases, compressible flow cases, incompressible flow cases, heat transfer, financial. So there is actually a Black-Scholes solver to solve the Black-Scholes equation, this financial derivatives PDE. That's more just an example, I guess. Multi-phase is if you have water and air, like waves and things like that. There's some stress analysis cases as well, electromagnetics. Discrete methods is to do with particles. So if I go into incompressible and then I ls, normally then they arrange by solver. So these are all incompressible solvers. So SimpleFOAM is one that we will use. So this is the simple algorithm like you would do for steady state flow, turbulent flow, in Fluent. But we use IcoFOAM as a simple laminar piezo algorithm. And there's piezo, pimpeller variants as well, and some other cases. So if I go into SimpleFOAM, ls there, these are all example cases. So there's this motorbike test case, which I think we start from that for the last OpenFOAM lab case. So this is a CAD model of a guy or girl sitting on a motorbike with flow going over them, and it shows you how to do like a full kind of industrial case. Pits daily, I can't remember. I think we run this in Fluent as a flow over a backward facing step, so that's already set up as well. You can see wind around buildings. You can kind of guess by the name what they are. So if I go back out of here and I go into IcoFOAM, so the first case we're going to look at is this cavity test case, this one here. So an OpenFOAM case, and by an OpenFOAM case, I mean the model. So normally for most softwares like Abacus or Fluent, the model is just underneath all the GUI, it's just one file, and the file just defines the mesh. which are all the coordinates of the nodes, how they're connected in terms of elements or cells, and then boundary conditions, material properties, other settings like that. Whereas in OpenFOAM, the models all take this form. So when you start with a model or case, it's essentially just a directory, in this case, this cavity directory, that contains 3 subdirectories, 0, constant, and system. So all OpenFOAM models have this same structure. So the constant folder is where the mesh is situated, and other things, I guess the name they come up with constant is things that were originally stayed constant in the model. So originally they probably didn't have moving meshes, so the mesh would have been on in this constant folder. And things like material properties will be defined there. System is things like the time step, the end time, and discretization schemes like first order, second order. And then 0 represents 0 time. So the fields you're solving for, you give their initial conditions and boundary conditions at 0 time. And then when the solver runs, it will print out the results at new times. So like 0.1 second, 0.2, 0.3. And then you'll have a software like PowerView to visualize those. So I think if I go 3 inside this, yeah, okay. So inside this directory, inside 0, we have U and P. That represents the velocity and pressure files. They're the primary unknowns for a laminar Navier-Stokes, incompressible Navier-Stokes problem. In the constant folder, we have transport properties. That's just a general name basically to define the viscosity or something like that. The mesh hasn't been created yet. And then in the system, we'll have the control dict and these FE schemes and solutions. And this control dict defines things like the time steps. This is setting between like first and second order schemes, and these are to do with tolerances and relaxation factors and things like that. In this simple case, using a very simple measure, which the second tutorial or the second lab is based on, we use something called block mesh. So block mesh is a simple measure which reads a file called block mesh dict. And this block mesh dict is a simple way to define block structured or mapped meshes. So you give the coordinates of the blocks and how many cells you want in each one. And if you run block mesh, it reads that file and then it creates the mesh. So if I go 3 again now, it makes a folder called polymesh, a polyhedral mesh, and it has all these coordinates. So I open up this case in PowerView. In Mac, I just define an alias just to correctly open up PowerView. I'll give that a second to open. I can look at the case. If in the meantime, if I open up some of the files, so Emacs constant transport properties, you'll see that it has some heading, and then new is just the kinematic viscosity. If I open up the control dict, system control dict, you'll see that it has this kind of key value setup. So delta T is the time step, which is 5 milliseconds, and 0.5 is the end time. And then there's some settings about the precision that is written out and some other things like that. If I open up FE schemes, this is, you'll start to see where this aligns with settings in Fluent. So you'll see there's the DT scheme. So this is first order Euler. And these are the gradient schemes, which you can also set in Fluent. These are the version schemes set in Fluent. So this Gauss linear is called second order central differencing. And then there's some other schemes that can be set here as well. And FE solution, you'll see that there's essentially a tab in Fluent that lets you set these tolerances as well. So if I look in PowerView, I press apply. So this is this PowerView software, which is just a free software that you can use for, it's not just used for OpenFOAM, it's used for other codes as well. So at time 0, you can see the initial velocity field is in the X direction, all at a constant value of 1, and then 0 all around the wall, and we've no time results yet. If I go back to the case, in this case, you run the solver with IcoFoam. That's it printing all the residuals like you would see in Fluent as a graph, except now it's just printed to the screen. If I ls the case again, now instead of just time 0, I have results at time 0.1, 0.2, 0.3, 0.4, 0.5. But in the control dict, it was solving at every 5 milliseconds. So there must be a setting in the control dict just saying, just write the results only every 0.1, not every time step. You can go back to PowerView, I can refresh. Now I've got these time steps. So it's not too exciting in this case. But if you play it, it's essentially you get like circulation of flow in the cavity. Oh, that's not the one I wanted. Where's streamlines? We do this one. Ah, great. Okay. I'm going to crash my computer because the defaults are probably set to too high. Right, while that's crashing, I'll look at this in case. So then the last thing to show, in the zero directory, if the way boundary conditions are set up, if I look at velocity, you'll see there's a name for each of the boundaries that came from the mesh. So there's the moving wall, and the velocity is set to be fixed at 100, so 1 meter per second in the x direction. And then the fixed walls are set to no slip. Whereas if I looked at the P file, it's just set to 0 gradient on the walls, which is like a normal wall condition. Yeah, Barbie's graph. So, very good. I'll stop there then. Thanks so much.